Okay, so next what we are going to start is the dynamic programming solution technique for unit commitment problem. So in the dynamic programming problem, uh, we start with some of the features associated with the dynamic programming problem. So as I said, I have already mentioned some of the terms, like what is a state. Okay, a state is nothing but a combination of the units which are available or which are actually present in a power station. Okay, so let's say you have 3 units. Say among the 3 units, which of the units, some of the units will be turned on and some of the units will be turned off. So the combinations among the units, among the different units, some of them turned on and some of them turned off, these combinations are actually known as the states. As I showed for the last example, for the 3-unit system, there we considered about 7 states, 7 possible states. Okay, and we also saw that not all of these states are feasible. So in this state, we can have some of the units operating, that means they are on, and some of the units are off, that means they are rested or they are offline. Then there is another thing which is known as the startup cost. And the startup cost for this lecture part, we will consider that the startup cost of any unit, it is not dependent on time. Okay, in other words, it is actually some fixed amount. By time here we mean the offline time, the time duration for which the unit was turned off or kept off. So that actually comes, that thing actually affects the pattern or the type of startup cost. Remember, we talked about the hot start cost and the cold start cost. Okay, and when we talk about the hot start cost and the cold start cost, the time the unit has been turned off has to be taken into consideration. However, for the first part of the solution using dynamic programming for unit commitment problem, in the first part, we are not taking into account the startup cost or the effect of the time duration for which the units were turned off. That effect or that duration is not actually taken into account. Rather, we are considering that the startup cost is a fixed amount, not dependent on time, offline time. And we also consider that there is no shutdown cost. Okay, and we also consider that at each interval, considering, let's say it is a 24-hour period problem for a day, so there will be 24 such intervals. If I take 1-hour interval, that is the load, that is if I take the load changes in each hour, so the hourly load variation, if I consider that, so in each interval there will be some minimum amount of unit capacity that should be available. Okay, so in other words, we cannot assume that all the units, let's say if there are 3 units, this line actually means that, well, if this is unit 3, unit number 2, and unit number 1, so all of the units cannot be turned off simultaneously. Okay, so that is not a feasible state. Some capacity should be made available at each interval. Feasible state, I have already talked about the feasible state, so I don't want to go here. Feasible state means the units. Okay, let me go through this. So the committed units can supply the required load. So that means if the load demand is, let's say 550 megawatt, and if my unit combination is this, let's say 3, 2, 1, and let's say I choose 0, 0, 1, and that means this is actually turned on, unit number 1 is turned on, but however the unit number 1 maximum capacity is 400 megawatt only. So that means if I run only unit number 1 to satisfy 550 megawatt at any interval, then it is not a feasible state. That means this combination or this state. So this is a state. So this state 001 can only produce 400 megawatt because unit number 1 maximum capacity is 400 megawatt. So that is not sufficient to supply the demand. So the committed units in this case are not able to supply the required load. So this is not a feasible state. Okay. And similarly, we have to also take care of this thing, that the minimum capacity, minimum amount of capacity for each period has been met, okay, by the units which are turned on. So the state, that state should also satisfy a state. Any state to become a feasible state should satisfy this criteria also. We'll see how actually that reflects in our calculation. So what is the formula or what is the algorithm? This is basically a recursive algorithm, very simple. Okay, nothing to be actually very bothered about all these symbols. Once we start the solution, probably you won't feel too bad about all these symbols, okay, appearing here. So let's go through the expression. So this is the very basic expression for dynamic programming problem. On the left hand side, we have one part of the expression, that is f cost k comma I. What is f cost k comma I? The f cost k comma I is basically the least cost or the lowest total cost to arrive at state ki. What is k and what is I? Let's see. K is basically nothing but the interval. Okay, let's say if it is an 8-hour problem or 24-hour problem, and if we are taking 1 hour sampling, okay, 1 hour interval. So each interval k equals to 1 means hour number 1, k equals to 2 means hour number 2, k equals to 3 means hour number 3, and so on up to 24 if it is a 24-hour period problem. I is basically the state, okay, the combination of units, nothing but the combination of units 001, 01, 01, 00, whatever. That is basically one of the I's. So the F cost basically will be calculated as the minimum cost to reach at a certain hour or a certain interval with a certain combination or with a certain state. Okay, we'll see how we are going to calculate this F cost. Then come to the right hand side. So you can see F cost is some minimization issue. Okay, some minimization issue. F cost is some sort of minimization issue with respect to L. Among some available L, we are going to calculate the minimum to get the F cost. Okay, so what is L? We'll talk about L a little bit later when we reach here. Okay, so let's start with P cost. P cost is basically nothing but the production cost for state Ki. Okay, for the state Ki, or the combination, we can say combination I, hour number K. The production cost for this Ki. How we are going to calculate it? Again, we'll show it in the example. S cost. So the S cost, it's a little different than P cost. How is it different? Let's see. So it is basically a transition. You can see K minus 1 comma L. So K minus 1. So we are having our transition from K minus 1 to K. So K minus 1. If K is the current interval, I said K is nothing but the hours. If it is taken in hours, intervals, hour based intervals. So if it is K equals to 1, 2, 3 up to 24. So if K is 2, then K minus 1 means the first hour. K equal to 2 means the second hour. Okay, so K minus 1 will be 2 minus 1. That is the first hour we are talking about. So because we have to make transition from hour 1 to hour 2 to hour 3 to hour 4 up to whatever amount of hour is under our consideration or in our consideration. So this transition, how much cost is actually associated when we are making the transition from, let's say it is K equals to 0 k equals to 1, k equals to 2, and so on. Okay, 4, 5, 6, 7, 8, like this. So how much cost is associated in each transition or in each state transition? Okay, so it is k minus 1 and k is okay, it's done. What is L and what is I? I, as I said, it is one sort of combination, or it is some sort of states. L is the state in the previous hour. So in the current hour, the combination that we are choosing finally is denoted by I, and the previously chosen combination we will denote it by L. Okay, so in the current state we call it I, where we are now. So if the current state is k equals to 1, if we are at the interval number 1, so the state combination that is chosen is I, and in the previous hour the same thing we call it L. We'll see actually in the calculation, whenever we go into the problem solution. I think everything, all the terminologies, all the symbols will become clearer, so just bear with me. So the f cost k minus 1 L is simply the f cost at the previous interval at k minus 1 with combination L. Okay, so state transition is we are having the transition from k minus 1 to k, and we are having transition from L to I. So for this, how much cost for doing this, how much cost will be there? So that is S cost, the transition cost. Okay, so now with all these little terminologies being introduced, we are slowly actually going for solving one problem of unit commitment using this recursive algorithm. Okay, so let's see. Okay, before we start the problem solution, there are a few more things to be discussed, like the symbol X and the symbol N. So in the dynamic programming, we will have a search path. That means the search path for the optimal solution. So this search path means we are looking actually for an optimal solution. So what is the path, or what is the trajectory through which, or the trajectory that we should follow for obtaining the optimal path from our starting point to the ending point? Okay, so that is the search path. And a strategy, what is the strategy? How we are having our transition getting done at each state, or at each interval, sorry, at each interval between the states. So what is X? X is the number of states to search at each period. So you can see clearly, this is our X. So let's say at interval k plus 1, this is interval k, the current interval, this is the previous interval, this is the next interval. So these are the intervals. At each interval, you can see at each interval, you can see several nodes, 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the 5 nodes are actually nothing but the different states. Okay, different states. So then what is X? X is basically the number of states to search each period. Means, let's say if there are 3 units in total, if we are not following any priority list ordering, then there will be 7 possible states. So among those 7 possible states, are we going to search through all of the 7 states or what? Okay, that decision will be taken care of. That number is actually reflected by X. So here you can see all the 5 nodes, 1, 2, 3, 4, 5, all the 5 nodes starting from here up to here are actually denoted by X. So here, let's say all the 5 nodes, we are actually searching at each interval, 2, 3, 4, 5, 1, 2, 3, 4, 5. So X remains as 5 in this example, in this diagram. What is N? The number of strategies or paths to save at each step. So N can be exactly the same as X if n and x are same, then n would also be 5 for this example. N could be something less than x, means how many paths, how many alternate paths for our progress or for our strategy we are going to store. Okay, so here in this example we are only storing 3, not 5. So if we store all the states which are in x, then of course it will take up some of the memory. Okay, so there's a memory issue. If I store very small number of states, that means instead of 3, let's say if I store only 1, okay, because we are talking about saving the memory storage. So if I choose 1 instead of 3, then of course I can save the memory at each interval. However, I might lose some very significant information or critical information. Okay, if I choose a very small number of path strategy or path to be saved at each step, I might lose some crucial information along my path, and it might end up that at one stage I would not be able to progress any further if the value of n is too small. So there are problems at both ends. If n is too big, there is memory storage issue. If n is too small, you might lose some critical information, lose some crucial info about the progress, and it might end up with some with some position or at some stage, at some interval, you might find that the further progress, because we saved a very less number of information, okay, we saved a very low amount of information at each path, at each interval. That means if n is too small, then you might end up with a position where you cannot progress any further with your solution. No feasible states are available further if n is too small. So we have to have a balance. We cannot go for very large n, we cannot go for very small n. So we have to stay to some intermediate values. Okay, and that again, that number will vary from problem to problem. We cannot say directly that what is the optimal value of n. Okay, so with all this information, let's start with a new problem, new example. So we have a unit, we have a set of units. The description of the units are available in this slide. So the fuel cost here is given in dollars per MBTU. That is same for all the units. Okay, the fuel cost is the same for all the units, unlike the previous examples. We have 4 units, 1, 2, 3, 4. The maximum is given here for each of the units. The minimum is given here for each of the units. The incremental heat rate in British thermal unit per kilowatt hour is given for each of the units. The no load cost is given. Means what? The no load cost means even if the unit is not supplying any demand, okay, not supplying any demand, even then there will be some cost. Okay, that is no load cost. For example, even if the unit is not running, actually you are running the whole power station, so you have some employees, so you have to pay the salaries and the wages for the employees. There are some maintenance work that are to be done for each of the units on a routine basis. So these are the costs which are not actually related with your production. So even if you are not producing anything, let's say you are not running a unit and the unit is under maintenance work. So your crew is there, they are working for you. You have the maintenance work. So these are the costs which you have to spend even without any generation for any specific unit. So those costs, you can say it like a cost which is not dependent on the generation. Okay, a fixed cost, you can say. Then you have the full load average cost, and we have already shown in one of the earlier examples that how we are going to calculate the full load average production cost. Here it has been given directly, sorry. Then the minimum uptime and minimum downtimes are given. As I said, the minimum uptime is the amount of time, the minimum amount of time that we should allow the units to be run. Once it is started, let's say if unit 1, you are deciding to start unit number 1, then you should allow at least 4 hours for it before you decide to turn it off again. Okay, similarly for unit number 2, once you start unit number 2 at any interval, then you should allow minimum 5 hours for it before you decide to turn it off again. Similarly, this one and this one. Whereas the minimum downtime says once you shut down unit number 1, then you should allow 2 hours before you again decide to turn it on again. Okay, 3 hours. That means for unit number 2, minimum downtime is 3 hours. It means once you shut down unit number 2, then you should allow 3 hours before you again decide to turn it on again. Okay, so these are the descriptions for minimum uptime and minimum downtime for each of the units. Now another information table is there, which is about the status and the startup costs. The status for all the 4 units means what is the current status regarding on or off or online or offline for each of the units present. So minus value means here, okay, -5. It means for the last 5 hours, unit number 1 has been turned off. +8 for unit number 2 means for the last 8 hours, unit number 2 has been turned on. Similarly for this one, for the last 8 hours, unit number 3 has been turned on. For the last 6 hours, unit number 4 has been turned off. The startup costs are there, the hot start cost and the cold start cost for all the units. Interestingly, for unit number 4, there are no unit startup costs. So probably this is one example of quick start unit. Okay, so there is no startup cost associated with it. And the startup hours, you can also see that there is no startup hours required. Cold hours means once the unit has been turned off and it has become completely cooled down, it will actually take 4 hours to get started again for unit number 1. For unit number 2, it will take 5 hours. Once it is cooled, completely cooled, then it will take 5 hours to get started again, to be ready for production again. Again, unit number 3, same thing. Once it is being cooled, then it will take 5 hours to become available for production again, once started from the cool status. Okay, so that means currently, before we start the problem, we know that which units are available to us or which units are actually producing. So unit number 2 and unit number 3, they are available online. So that means they are producing or they are generating. Whereas unit number 1 and unit number 4, they are not producing. So the combination would be, if this is unit number 4, 3, 2, 1, it would be 1, 0, okay, 1, 1, 0. So unit 2 and 3, they are on. Unit 1 and 4, they are off. Whatever, you can also take like this sequence, but it remains the same, 0, 1, 1, 0. Unit number 1 is off, unit number 4 is off, whereas unit 2 and unit 3, they are on. So this would be the state, initial state. This is the load demand. Okay, so the demand is varying, and the problem is actually here, it is an 8-hour long problem. So you can see in hour number 1, the demand is around 450. In hour number 2, there is a jump, and it is around 530 maybe. And unit hour number 3, the demand further jumps to 600 megawatt. Hour number 4, it drops back to probably 540 or 50, something like that. Then hour number 5, the demand further drops, comes to 400. Hour number 6, it further drops less than 300. Unit number 7, there is a slight jump. So it is very near to 300. and then our number 8, there is a further jump and the demand goes to rises up to 500 megawatt. So this is an 8-hour problem. So to start with the solution, we prepare a capacity ordering of the units. So this is not priority ordering, remember, this is capacity ordering. Capacity ordering means first we can always go for the binary ordering. Okay, the binary ordering means simply it would be 0 0 0 1 0 0 1 0 and so on. Okay, so the binary ordering we can easily do it. So where is 0 0 1 0? Let's see. 0 0 1 0. So you see this is 0 0 1 0. So if I do the binary ordering, then the expectation would be something like this. The ordering would be something like this: 0 0 1 0. Then so this is 1. If the binary ordering were done, this is 2. Then 0 0 1 1. This is number 3. 0 0 1 1. So this is number 3. So you see all the binary orderings are actually present here, but the binary ordering is not being followed here because we are not looking for the binary ordering among the units. Rather, we are looking for the capacity ordering. What the capacity ordering means is that, okay, you can always go for the binary ordering just to make it easy to start with. You can always go for the binary ordering. And then for each of the states here, that means among the combination, whatever the combinations we are talking about, each of the combinations are actually giving a certain number, and that number is actually the state number. Okay. So in the binary ordering, you can always go for the unit combinations in the binary manner, in the binary sequence. So your first one would be 0001, and 0001 will give you the maximum capacity of 60. Okay, 60. 0010, how much does it give? It gives you 300. 0011, it gives you 360. 0100, how much does it give you? 0100, it gives you 250. Okay, 250. Okay, don't go any further because we are in a position where we can make the difference between capacity ordering and binary ordering. So if I follow the binary ordering, you can see up to this point, there is a nice increase in the capacity. However, when I reach here, there is a decrease in capacity. So now this sequence, whatever sequence we have shown here, this is a binary ordering, but this is not a capacity ordering because here the maximum capacity is actually fluctuating. It is getting up to this point, and then is again getting down. Okay, going down. In the capacity ordering, we will rearrange the binary ordering. We will actually rearrange the binary ordering in such a manner that the capacity is always increasing. Okay, it is always going in the ascending manner from bottom to the top. So the state number will only be assigned. The state numbering will only be assigned once we complete the capacity ordering. So when we are going through the binary ordering, we are not going to assign any states. Actually, the state numbers will only be assigned after we rearrange the unit combinations in such a manner that the capacity is increasing only, unidirectional increase of the capacity. It's not like this 60, 300, 360. Up to this was fine, but then you see it is 250. Okay, so the capacity is reducing suddenly. We are not going to follow this scheme. Okay, if I follow the 5, let's say how much 0 1 0101. So that is 5. 0101. How much is that? 0101. Okay, so you see 310. Okay, 0101. So you see 310. Again, this is higher than this, but this is lower than this. So you see it is a complete, it is completely out of sequence. Okay, considering the maximum net capacity combination. Sometimes it is increasing, then it is decreasing, then it is again increasing, but again this one is less than this one. So we are actually getting the ordering done based on the maximum capacity. Okay, nothing else. And then we are providing the state number. So this is capacity ordering. This is not the binary ordering, remember. But we have to take help of the binary ordering at first. Only then we can get the capacity ordering. So we start with the binary ordering without providing the state numbers. Then we rearrange the binary ordering. That is, the unit combinations are rearranged such that the maximum net capacity is increasing only from bottom to the top. And then we assign the state number. So assigning the state is the last stage here for the capacity ordering table. Okay, so there are several cases that we are going to take into consideration. We start with case number 1. So in case number 1, what we do, we actually follow the strict priority ordering. Okay, so what is priority ordering? We have already said. Then the next point, we are going to ignore the minimum uptime and downtime of the units. Okay, so then the startup cost is only the cold start cost. So there is no hot start cost. So only the cold start cost will be taken into account while we are calculating or while we are solving the problem. So that means the cold start cost will be taken into consideration. The hot start cost is not taken into consideration, of course, for case number 1, remember. And also for case number 1, the minimum uptime and minimum downtime are not taken into consideration. So that constraint is actually neglected for case number 1. So you can say this is a pretty much simplified version. Okay, we are following the strict priority ordering. So that means many of the available states will not be feasible because of the priority ordering. We are ignoring uptime and downtime. We are not considering hot start cost. So many assumptions are there. Many simplifying assumptions are actually associated here. Okay, so case number 2, we will update the first one. That means we are not going to stick with the priority ordering. Rather, in case 2, we are going to follow the complete enumeration scheme. So here, all the available states could be the feasible state if it is satisfying the demand only. Okay, so no priority ordering is maintained here in case number 2. Again, this is the same as case number 1. This is the same as case number 1, and this is the same as case number 1. So the difference between case number 2 and case number 1 is only in the first point. Here in case number 1, we follow the priority ordering, but in case number 2, we are following a different scheme, that is complete enumeration scheme. All the available states will have a chance to play. Okay, we'll have a chance to be to get selected. Of course, if that state has sufficient capacity for satisfying the demand. Case number 3 is the most complex one here. So here again, like case number 2, we are following the complete enumeration scheme. Here we are going to not ignore the minimum uptime and downtime. In case 3, we are going to consider the minimum uptime and downtime. And also we are going to consider the hot start costs. And here there's a little explanation when we should take the hot start cost and when we should take the cold start cost. Okay, so let's go through these 2 points shortly. What is hot start cost and when should we take hot start cost and when we should take cold start cost. The cold start cost we should take whenever the unit has been turned off for a duration let's say for unit number 1, we should take cold start cost if it has been turned off for 4 hours or more. Okay, that means let's say unit number 1, currently what is the status? The status is off. How long it is off? It has been off for 5 hours. So now that means for the cold start cost to be considered, the unit has to be completely cooled down. Okay, so how long it has been off? It has been off for 5 hours. What is the startup time? The startup time is 4 hours. So this 5 hours is greater than the 4 hours. So now if we are going to start the unit all over again, we have to look into this value 5 hours. We have to check it against this value, that is 4 hours. So if you are going to turn it on, so which startup cost will be associated? The cold start cost will be associated, but because the unit has been turned off for such a duration which is higher than the startup hours, cold start hours. Okay, so now the startup cost, if I turn unit number 1, if I turn it on, if I decide to turn it on, the startup cost has to be taken as 350 instead of 150. However, if that value is less than 4, this value is less than 4, and I wish to turn it on again, then I have to go for the hot start cost. Okay. So in this manner, I can choose between hot start cost and cold start cost. So that has been explained here. So this is what I meant. Okay, this is what I meant. If unit downtime is greater than or equal to unit cold startup time. So if unit downtime, you see unit downtime is 5 hours. For the last 5 hours, unit has been down. It is equal to or greater than the startup hour, cold startup hour for the unit. So it is greater than here. 5 hours is greater than 4 hours. So you have to go for cold start cost. Otherwise, you can go for hot start cost, but you have to keep in mind whether you can run the unit on or not. That will be actually decided by the minimum uptime and downtime. Okay. So for hot start cost or cold start cost, actually, first of all, you have to be able to run the unit. Okay, to run the unit. So the unit was turned off. The unit was turned off, let's say for 2 hours. Okay, let's say the unit 1, it is turned off for now. It has been turned off for 5 hours. So the 5 hours is actually higher than 2 hours. Okay, so that means unit number 1 has satisfied the minimum downtime constraint. It has been down for an hour, for an hour, for a value, for a duration, actually, sorry, for a duration of hours, which is 5 hours, and which is higher than minimum downtime, which is higher than 2 hours. So that means you can turn unit 1 on if required. Okay, you can turn unit 1 if it is required, because the off time is greater than the minimum downtime. So because it is 5 hours, that is higher than 4 hours, when we start it, the cold start cost would be there. So what is the example, or what would be the scenario when we have to consider the hot start cost? The scenario would be such. Okay, so let's say if unit number 1 is or has been turned off for 3 hours. Okay, so if it has been turned off for 3 hours, does it satisfy the minimum downtime? Yes, it satisfies the minimum downtime. Actually, of course, in fact, if it is off for 2 hours, that is fine. But now we see it is off for, let's say, 3 hours. It is off for 3 hours. So the minimum downtime constraint is satisfied because 2 hours is enough, but it has been turned off for 3 hours. So if it is required, we can turn it on because minimum downtime is satisfied. Now, when we decide to start it, which cost should be there? Now you see for 3 hours, it has been off, which is less than the cold start hours, cold startup hours. So it is less than 4 hours. That means it hasn't been off for 4 hours. It has been off for 3 hours. So it hasn't cooled down completely in these 3 hours. For getting cooled completely, it will take 4 hours. Okay, so now if I want to run it again, so I have to go for the hot start cost. That means some temperature, some heat is still there associated with the unit. It hasn't been cooled down completely. So because some heat is already there in the boiler, so you don't have to spend that, don't have to spend this much of money to, let's say, take the temperature, if the cool temperature, let's say, is 0 degree, just for an example, 0 degree to 2050 degree Celsius, just for an example, this is the cool down temperature, cool, and this is the completely hot, completely heated up. This is the cool down. So 0 degree Celsius means at least 4 hours has been elapsed. Okay, let's consider it in this manner. At least 4 hours has been elapsed once the unit was off. So if 3 hours has elapsed, it is somewhere here. Hour number 1, hour number 2, hour number 3, hour number 4. So if 4 hours is gone or more, 5 hours, doesn't matter, then it is 0 degree. 0 degree, 6 hours, 0 degree. Okay. But anything less than this, let's say 3 hours as it is here. So it is somewhere around, let's say 500 degrees Celsius, let's say. So you don't have to spend that much of fuel, which you would have to do if it were at 0 degrees Celsius. So this heat rise will cost more money than this heat rise required. So this is cold start cost, cold start. This is hot start. Okay, I hope it is clear. And of course, you have to make sure the minimum downtime is maintained. So minimum downtime for unit number 1 was 2 hours. So of course, the unit has to be turned off for at least 2 hours for making it ready to be turned on again. Okay, that value is mentioned in minimum downtime column in one of the previous slides. Okay, so I hope it is clear. So how much was it? 5? Yeah, it was 5. Okay, so let's make it 5 back again. So this was 5. Save it. Okay, so this is about the initial status, and this is about the case number 3, where we have to also consider the hot start cost. Okay, I mean, besides the cold start cost, we have to also consider the hot start costs. So in this example, we are following the simplified unit characteristics. So now the units are represented by a fixed cost. So the unit cost is no more a quadratic function, rather it is a straight line function. So we have the no load cost. So you can see the no load cost is there until and unless the minimum generation limit has been reached by any unit. So along the x-axis we have the P, that is the production. Along the y-axis we have the cost. So in the no load cost, it continues. Let's say if P is 0, there is no load cost. If that increases P min, that means between P min and P max there is a linear rise. There is a linear rise in cost. And if you extend it back, if you trace it back, then you get a point where you reach. I mean, if you follow the trend, follow the slope, ultimately you will get a point which will intersect the y-axis. So that point is your no load cost. Okay. So no load cost plus incremental cost into P. So this slope is basically the incremental cost. This is your incremental cost slope. So FP is basically the no load cost plus the incremental cost, that is the slope, into the P value. Okay, so that will give you the FP numeric value for FP. So this is a straight line function, simplified function, not a quadratic function. Okay, so we'll start with the solution now. We have the preliminary calculation. So in the preliminary calculation, what we do, we first calculate the unit incremental cost. So how we are going to do it? The incremental cost in dollars per hour is nothing but the incremental heat rate. So the incremental heat rate is given, already given. So these values are given. And that is the unit is given is British thermal unit per kilowatt hour multiplied by the fuel cost. So the fuel cost, as I said, for each of the units, the fuel cost is assumed to be the same. That is given also in the problem statement, the very first slide of the problem statement. So let's go here in slide number 30. The fuel cost is $2 per MBTU. So that is given. Okay, so it is listed here. Then incremental cost is calculated as the incremental heat rate multiplied by the fuel cost. So you see the units are to be manipulated now. So units are to be adjusted actually. So you have British thermal unit here. You have millions of BTU per hour here. So 10 to the power 6 will be there to convert between British thermal unit and millions of British thermal unit. So take care of that million part here. We are including the 10 to the power 6 in the denominator, and in the numerator you see we are going to have a conversion from kilowatt to megawatt. Okay, kilowatt to megawatt. So in this manner we are getting the final unit as dollars per hour. Okay, so finally the incremental cost is written, is calculated in short as IC, so that is in dollars per hour, and you can see the incremental cost for unit number 1 is 20.88, and all other unit values are actually given here. Now we go for the priority ordering in case number 1. So as I said in the previous example, in the priority ordering we cannot choose all the states possible, rather we have to follow the strict priority ordering. So what is the priority? We follow the same principle, like we have the full load average cost. So the full load average cost is actually given in the main problem statement, probably in slide number 30. Yeah, so you can see, so according to this column we have to choose what is our top priority unit and what is the bottom priority unit. The topmost priority unit should be unit number 3. Next one should be unit number 2. Next one should be unit number 1, and the last one should be unit number 4. Okay, so accordingly we prepare the priority list ordering. So unit number 1 should be turned on first. Unit number 3. Okay, we have repeated it here. So unit number 3 is the top priority, so unit number 3 should be turned on first. So this is unit number 3. You cannot turn on any other units before you turn on unit number 1. So here actually these are the states that we talked about, and this is these unit combinations are actually following the strict priority ordering. So let's check some of the states which are not actually picked here. So let's check state number 1. So where we see that, well, unit 4 is turned on. So unit 4 cannot be turned on because before any other units, because it's the least priority unit. So that is not feasible. It's not a feasible state according to priority list ordering, of course. Unit 2, state 2, you have to turn on unit number 1, but this is priority. In the priority list it is number 3, so you cannot do it. 3, state 3, can we do it? Okay, we have unit combination 1 and 4 available, but of course these are the last 2 prioritized units, so that cannot be also taken into consideration. Similarly, you can check all the other combinations, and finally you would find that the first allowable state is number 5. Okay, where the first priority unit is being on, that is unit number 3. Next, unit 3 and unit 2 will be on. So where we find it, unit 3 and unit 2 on, and unit 1 and unit 4 off. So that is combination number 12. Unit 2 and unit 3 on. Okay, unit 2 and unit 3 on. The next one would be unit 3, 2 and 1 on, whereas unit 4 is off. So 2, 3 and 1 on. 2, 3 and 1 are on, unit 4 is off, so that is state number 40. Next, you should pick it. And the last one, the last priority should be all the units are turned on, because you have taken care of all the higher priority units in state number 14. So the last one remaining is all the units on, that is state number 15. Okay, and the last column over here gives you the maximum net capacity. That is simply summation of all the maximum capacity of the available units in each state. So if you add them up, then you get this value on the rightmost column. So that's pretty simple. So the allowable state we find here is state number 5, state number 12, state number 14, and state number 15. Okay, So let's go forward. Next, among the allowable units, what is the initial status? The initial status, remember, in the initial status, we found that our unit 2 and unit 3 are on. Okay, unit 2 and unit 3 are on. So, and unit 1 and unit 4 are off. Is it feasible? Is it allowable state? Is it an allowable state? Okay, let's check. Well, this is an allowable state because unit 2 and unit 3 are on and unit 1 and unit 4 are off. So we can start with this. This is the initial status given. So actually we are sitting at this point now. Okay, we are sitting at status, or our status, current status is state number 12. Okay, following the initial status. Okay, so first we take up the example for case number 1. So in the case number 1, we start with our number 1. What is the demand? The demand is 450. That is picked from slide number 32. Okay, so this is 450 megawatt. So this is the demand. Initial condition. Now this initial state is being denoted by L. Okay, so now slowly we'll be getting used to all these symbols. So our first hour, the first interval, K equals to 1. The initial status L, it is 12, 0, 1, 1, 0. That means unit 2 and unit 3 are on, unit 1 and unit 4 are off. The load is taken from the load, the daily load profile or the hourly load profile, 8-hour hourly load profile, that is 450 megawatts. The feasible states, feasible state is 12, 14, and 15. So there is a difference between feasible state and allowable state. Although in the allowable state list, we found there are 4 states, that means 12, 14, and 15, as well as 5. But remember, you have to satisfy a demand of 450 megawatt. But unfortunately, your state number 5 is unable to provide that much of megawatt. So you see the capacity is only 300 maximum, which is not sufficient to satisfy 450 megawatt. So from the allowable states, following the priority ordering, we found that 4 states are allowable. However, when we check the capacity of each of the allowable states, we find that state number 5 fails to satisfy the maximum, fails to satisfy the demand of 450 megawatts. So that state 5 will be excluded from the feasible states list or feasible states set. So due to the capacity limitation, we exclude number 5 state, okay, state number 5. So we are only left with 3 probable or feasible states, 12, 14, and 15. So now we have to start our journey from the initial condition or the initial state of 12. So you see L column gives us the initial state. Feasible states, what are the feasible states where the transition is possible? These are listed under the symbol I. Okay, so these are the feasible combination. That means we may jump from our initial 0110 status. We can either go for 12, or we can either go for 15, or we can either go for 14. Because all of these 12, 14, and 15, they are also candidate solutions because all of them can satisfy a demand of 450 megawatt. But which one is the most optimal? We have to search for it following the dynamic programming algorithm. Okay. So either we choose from 12, the initial status L12, we can jump from 12 to 12 for our number 1, or we can jump from 12 to 14, or we can jump from 12 to 15. So we have 3 different choices. So those choices are listed in the first 2 columns. Okay, so this is the transition from 12 to 15 is possible. 12 to 14 is possible. 12 to 12 is also possible. Which one to choose? That depends on the cost calculation. So let's go to the cost calculation part. Before that, let's check the unit production combination or unit combination. There are 4 units, 1, 2, 3, and 4. Now, if we are choosing 12, that means if we want to stay at 12, we were at 12. Our initial status was 12. We want to stay at 12. What would be the scenario? The scenario would be still unit 2 and unit 3 will be on. Unit 1 and unit 4 will be off. unit 2 and 3, how much will they produce? That is the next question. That is ELD, question of ELD, economic load dispatch. So here, what we are doing actually, the algorithm that we are following is pretty simple. We are not actually directly solving any ELD. Rather, we are following a simple step. The step is such. Okay, if unit 2 and 3 are on, which is the most economical one? The most economical one is unit number 3. So we will try to load the unit as much as possible at first. What is the capacity of unit 3? The capacity of unit 3 is, the maximum capacity of unit 3 is 300. The demand is 450. So what we are going to do, let's do it here. So demand is 450 for hour number 1. Unit 3, okay, we are running unit 3 and 2. So this is our decision. How much each of them will give? The lowest cost unit is unit number 3. It can give 300. Okay, can we take 300? This is the question. Okay, let's see what happens if we take 300. If we take 300, the remaining demand is 450. So how much remains? 450 minus 300. So 150. Okay, let's write it down first and let's check what is going to happen. Okay, so we are taking the maximum possible capacity of the lowest cost unit at first to satisfy the demand. However, we have to keep an eye on the remaining generation from the other unit. By keeping an eye means we have to check whether this value lies within the maximum and minimum limit of that specific unit. In this case, luckily, it lies between 250 and 60. So that means 150 is a valid choice. So we'll simply choose 300 from unit 2 plus the remaining load from unit, 300 from unit 3 and the remaining load from unit 2. In total, we will get 450 and that is done. Okay. So this is our choice of economic dispatch for this case at state number 12. Okay. Okay, our number 1. So state 12, you see 300 from unit 3, 150 from unit 2. In total, we get 450. What is the production cost? Production cost is simply you have to take the, because now you see we are simply taking the simplified cost function. Simplified cost function. So what is the simplified cost function? Straight line, this one, no load cost plus incremental cost into P. So let's go there. So no load cost. What is the no load cost? How much we are taking? 684.74 plus 17.46 into 300. So you see, this would be the no load cost. The no load cost. This is the incremental cost. And this is the P or unit. How much unit or how much megawatt we are actually taking from that unit. Okay. Similarly, this is the no load cost. So this is associated with unit number 3. And the same thing for unit number 2. So this is no load cost for unit number 2, incremental cost for unit 2, and the production from unit 2. Okay, so this is for unit number 2. So if you plug those values in to the expression of P cost, then we get this value. So this P cost 1, 12, it means this is our number 1 with state 12 being chosen. This is the meaning of this bracketed terms over here. So this is K and this is I. Remember in the DP algorithm, you had the first entry was P cost Ki. If you go back to that slide, we'll see P cost Ki. Where is that? In slide number 28, P cost Ki. So we are calculating P cost Ki. Okay, so P cost Ki is shown here 9208. So here you see 9208. And similarly, we can calculate for 14 as well as for 15. But how we are choosing the unit production for state 14 and 15? Let's have a look at those values first. Similar kind of algorithm will be, or similar kind of technique will be followed here. So let's pick number 14. Okay, so what is the transition between 12 to 14? When we have the transition, 14 means what? You have unit 1, unit 2 and unit 3 available, but unit 4 not available. Okay, so this is 0. Okay, now how much, again, what the question is, how much you should take from unit 1, unit 2 and unit 3 for satisfying a demand of 450 megawatt. Okay, so now you have to remember that we have to run unit 1, all 3 units. We have to run all 3 units. So when we run any of the units, we have to keep in mind that we cannot go beyond the maximum generation limit and we cannot go below the minimum generation limit. This is the problem. Okay, so now we have to take care of the minimum generation limit for unit 1 and unit 2. Let's see, where is the capacity? Yeah, here is the capacity. So now if we look at this capacity table, unit capacity table, we have to take unit 1, 2 and 3. The 4 is off, no problem. So again, we look, okay, the demand is 450, remember, demand is 450. Now the question is, our target would be to minimize the cost. Okay, so for doing that, we will always try to take up the maximum demand available from the lowest cost unit. So the lowest cost unit is unit number 3. According to this full load average production cost, unit number 3 is the lowest cost unit. So 300 we have taken, the remaining is 150. Remember, we have to run both unit 1 and unit 2 as well as unit 3 besides unit 3. So now we will come to unit number 1 instead of unit number 2, because we have to satisfy the minimum limit available from unit 1. Remember, among these 3, 1, 2 and 3, the least, or actually the highest cost, the costliest unit is unit number 1. So what we are simply doing, we are first, if there are 3 units actually, we are first picking the maximum possible from the least cost unit. Then we are jumping to the last or the highest cost unit. Actually, the highest cost unit, we are satisfying the minimum. Okay, because if I take anything more than this, that will actually increase the cost. So because I have to pick the minimum, otherwise I cannot run unit 1. Okay, if I decide to run unit 1, I have to at least take the minimum. Here I'm going for the minimum, because if anything more I'm going for, that will actually increase the cost. So the 25 I choose, 300 I choose because that is the maximum for the least cost, 25 is the minimum for the highest cost unit, and the intermediate, the remaining value I will take from unit number 2. So what is the remaining value? If I take 325, I will be left with 125. So in this manner, I am actually going for the economic load dispatch. Okay, shortcut calculation actually, not exactly solving the economic load dispatch using lambda iteration or any other standard method. That will actually take a long time to be solved, to get solved. So by hand calculation, it's not, I mean, it is possible, but it will take a long time. So we are going for a shortcut method here. Okay, so now we have 3 units for this state 14 that will satisfy 450. First we see that, well, 300 is possible, we can take 300, because even if we take 300, the remaining 2 units can take up some of the loads. Unit 1, this is the highest cost unit here, or the costliest unit here among these 3. So we take up the minimum, because we have to take at least the minimum from that, and the remaining part is taken from unit number 2. The remaining megawatt is taken by unit number 2. So the combination is unit number 1 gives 25, unit number 2 gives 125, unit number 3 gives 300. In total, they give me 450 megawatt. So this is the combination I'm talking about, 25, 125, and 300. And in the same manner as we showed here, in the same manner, you can calculate the P cost KI for this state 14. State 15, what to do? Okay, now we have to run all the 4 units. We have to run all the 4 units. So again, we check, okay, 450. The least cost unit is unit number 3. So you pick unit number 3 first and you take 300. It's possible because the demand is 450. Still you have 150 remaining. Okay. Go to the highest cost unit. Highest cost unit now it is 4. So you take the minimum from 4. Okay. Then the next highest cost is unit number 1. Take the minimum from it. Okay. Now you check how much is remaining. So it is 345. 345. Okay. How much is remaining? 450 minus 345. It is 100. Okay, 5 actually 105. Okay, 105. Now this 105, does it lie within the minimum and maximum limit of unit number 2? Let's check. We have to satisfy 105. Yeah, it is between 60 and 250. So okay, we are done. So we can take this 105 pretty easily because all the unit limits are within their valid bounds. Okay, upper bound and lower bound. So in total, you get 450. So you see, we take the minimum, take the maximum, and we take the remaining. Okay. So in this manner, all the bounds are satisfied for all the units that are to be run for combination for the state 15. So now you have P cost KI calculated for the 4 units running. Okay, so this P cost is done. Next is the S cost. Remember, there is the transition cost. So the transition cost, let's see what is the status change. So in 12 to 12, if I jump, our initial status was 12, remember. If I choose to jump from 12 to 12, if I choose state 12, then there is no bit change. Okay, it was 12. Here it is also 12. So K minus 1, this hour 0, that is actually the initial status. K, it is the first hour where the demand is 450. So K is 1. So this is the explanation of all this. So because here none of the units status are changing, because I'm staying at the same state number 12. I am staying at the same initial status. So none of the bits are actually updated. You can see it was 0, 1, 1, 0 in K minus 1 state, at K minus 1 state, or at K minus 1 interval. And here also in the first hour, I'm staying at 0, 1, 1, 0. So none of the bits are changed. So actually no state transition cost will be there. So 0 transition cost, because there is no change actually in the states. We were at 12 in hour number 0. We are still at 12 at hour number 1. So no transition cost. From 12 to 14, what is the change? This is the change. So from 12 to 14, 12 is this 0, 1, 1, 0, and 14 is 1, 1, 1, 0. So we have to run unit number 1 if I choose to have this transition from hour 0 to hour 1. If I want to have this transition, so my first unit has to be turned on. So that means I have to start unit number 1. Remember, in case 1, we are only considering the cold start costs. So what is the cold start cost for unit number 1? We have to check. So the cold start cost for unit number 1 can be found in slide number 31. So you see it is 350. So unit 1 startup cost, in case 1 we are considering cold start cost, that is 350. So in the table, you will see the entry of 350. So this is the additional cost that we have to take into account if I choose this transition from 12 to 14, from our number 0 to our number 1. Okay. The last one is the transition from 12 to 15, the first entry here. So in 12 to 15, what we will do in the 15, this is 12. The 15 is 1, 1, 1, 1. So now you see 2 bits are updated, 2 of the bits. The first one, the unit 1 and unit 4. So this is the transition and this is the transition. So unit 1, 2, 3, 4. So unit 1 has to be started, unit 4 has to be started if I want to have the transition from 12 to 15. So you see now what is the startup cost for unit number 4 and what is the startup cost for unit number 1? We have to add both of them. Let's go back to that slide number 31. So you see there is no startup cost associated with unit number 4. So that means unit number 4 will not have any additional startup cost. However, unit number 1 has some additional startup cost, and that is 350. So 350 plus 0, 350, that is the startup cost, cold startup cost for unit 1, plus 0, that is the cold startup cost for unit number 4, because we are talking about state 15 where we are starting on unit 1 and unit 4. So in total, that is 350. So you'll see an entry of 350 there in the table in case 1, hour 1. Okay. Okay. So here you see it is also 350. So now what is the F cost? K minus 1L. K minus 1L means what is the minimum cost? Remember, F cost is the minimum cost or the least cost. This is K minus 1L. K minus 1L means this is the in our number 0, at our number 0. At our number 0, we don't have actually any information. We only have the information about the state 12. So K minus 1L is actually, we don't have, this is the starting phase actually. This is the starting phase. So we start with some 0 cost information. We start with some 0 cost information. Our F cost will only be calculated from our number 1, okay, not from our number 0. So our number 0 cost are all assumed to be 0, flat start, 0 start. So the F cost Ki, this is the important thing here. The F cost Ki is how much? This plus this plus this, because this is 0. Remember, this formula is the DP formula, okay, DP algorithm. DP algorithm takes care of this cost plus this cost plus this cost. Because this is 0 here, so simply add up this and this, you will get this. Add this and this, you will get this. Add this and this, you will get this. So what is the minimum? Among these 3 choices, the minimum one is this. So means if we stay at number 12 state in our number 1, then we are choosing the minimum cost solution. So this is the solution for our number 1, the transition from our number 0 to our number 1. And that is being highlighted by the red color over here. Okay, so what are the currently saved states? Remember, that is denoted by N, and we choose to store only the 2 least cost strategies. So what are the 2 least cost? This is the least cost, and this is the second least cost. So we are not going to store all 3. We are only going to choose 2 of them. Remember, this choice is completely arbitrary here for the time being. It's completely arbitrary, and that choice might vary from problem to problem. Okay, you will only get the idea that what is the optimal solution only after you start the solution and if you progress with the solution. If you are stuck at some point before having the complete solution, in that case you have to loop back and increase this number. Okay, and increase this number. Some might say, well, why not choose only one? Because as I said, probably if you choose only one, you will not be able to finish the problem. Okay, from the beginning up to the end, you probably won't be able to finish the solution. You will be stuck at some point. You will find that, well, you are not able to progress any further, because probably you will not be having enough feasible states. Okay, if we choose only one, that is the minimum strategy is stored. You can save some space of memory for storage, but you are you are in danger of not getting enough feasible states at one of the stages of your solution. So what is the progress? The progress means you were at 12. This is the initial status. Now you choose your strategy. This is your strategy path. Your strategy is you stay at 12. This is k equals to 0. This is k equals to 1. So k equals to 0 actually we don't write because that is already given. We start from k equals to 1. So this is included in the progress list. Let's go to our number 2. Okay. Once we understand our number 1 calculation, the remainings are actually identical. Okay, actually identical. I will go through few of the hours. The remaining hours probably you would be able to complete it on your own. So our 2, let's take in detail for our number 2. In our number 2, our load demand has increased to 530. Okay. We previously saved the states, and that previously saved state are denoted by L. So now you know what is actually L. Okay. So you see the previously saved states were 12 and 14. Sorry, the current saved state are denoted by N. And when we increase the hour counter by 1, that N value is actually being transferred to the variable L, because you need to update your N here. So that N value is actually transferred to the L variable. That is the previously saved stages 12 and 14. The load demand has increased to 530 megawatts. The feasible states, what are the feasible states? You see, the load has increased. The combination 5, state 5 was unable to satisfy 450 megawatt because of its low capacity 300. However, 12, 14, and 15, we are choosing the priority ordering. So we only have 4 states available. So we can only choose among these 4. Okay, we can't choose 13 or 11 or 10. So that's why we are only talking about these 4 highlighted 4 states. 5 cannot satisfy actually the demand. Okay, because the demand is now increased to 530. However, 530 can be satisfied by 12, 14, and 15. So still in our number 2, the feasible states are 12, 14, and 15. State number 5, even now it cannot satisfy the demand. So that's why, due to capacity limit, state 5 is excluded from this set of feasible states X. Now the load has increased. So again, we start from okay, this 12. Okay, so now remember, L has to be updated now. In the first one, in the first hour, L was simply the initial state. Initial state is L, that is 12, that was given. Now L has been updated. L has now 2 different states, 12 and 14, 12 and 14, 12 and 14. So the transition could be from 12 to 12. So the transition would be actually between these 2. In simpler words, the transition would be between L and X. So these 2 sets can have interaction from 12 to 12, 12 to 14, 12 to 15. Okay, or from 14 to 12, from 14 to 14, and 14 to 15. You see, 12 to 12, 12 to 14, 12 to 15, or 14 to 12, 14 to 14, 14 to 15. So the transition would be between L and the feasible states X. We can also call this as I, as mentioned here. The states here, feasible states, we call them X, but once we list it here, we call it I. All the same. Okay, so the transition, these are the possible transitions. So now again, like the previous hour, we have to calculate the costs. And we have, before we calculate the costs, we have to know how much production will be available from each of the units. So let's do the same thing as we did from 12 to 12 or 14 to 12. So our okay, so from 14 to 12, 14 to 12, if it is 12, okay, we haven't listed it here. If it is 12, then of course we know that it is how much? 0 1 1 0. So that means this one and this one will have the entries, and we know the entries. It is 300 and 300 and okay, this is actually the previous state. So here we won't have any entry. Here we won't have any entries. This is the previous state. So the current state is the point of consideration. The current state is of the point of consideration. So if it is 12, we have to satisfy 530. So how we are going to divide it? Again, we have to choose the least cost unit first, that is 300. And the remaining part will be taken from unit number next available unit. So that is 230. So that gives you 530. Is it available from unit number 2? 230. Let's check whether it is within the maximum and minimum limits. It should be, of course. Yeah, so unit 2 can provide maximum of 250. So okay, 230 is possible by unit number 2. So we take 300 from unit 3 and we take 230 from unit 2. In total, this is the demand, 530. So we're talking about this. So 230 and 300, you calculate the P cost, you calculate the S cost. Okay, S cost, it is 14 to 12. Remember, it is 14 to 12. So from 14 to 12, what we have, what changes do we have? 14 to 12. 14 to 12, we have the change 14 to 12. So this is the change. 14, unit number 1 was on. 12, unit number 1 is off. This is from hour 1 to hour 2. Okay, K minus 1 to K, hour 1 to hour 2. This is the change. So you see here, instead of starting up, we have to shut down. If we choose to have the transition from 14 to 12, we have to shut down unit number 1. But in case 1, we are not including any shutdown cost. Actually, throughout the problem, we are not considering any shutdown cost. Okay, we mentioned it probably at the very beginning. There is no shutdown costs. There is no shutdown costs. So there won't be any additional charge for this shutdown. Okay, so, and none of the units are actually turned on. None of the additional units are actually turned on. So the additional cost, transition cost from 14 to 12 is actually 0. This is the P cost. So F cost K minus 1 L. This will now come from here. F cost K I at state number 14. Now this will become F cost K minus 1 L. So that is your 9843. Okay, state number 14. This is the previous state. This is the next state we are considering to go from 14 to 12. So whenever we were at 14, what was the F cost? K minus 1, previous interval, L, previous state. So this is the one. Okay, 14. When K was 1, this was the cost, F cost Ki. So you see, thus we are including this 9843 here. Okay, F cost K minus 1 L for state 12. Already we have the cost here. Already we have the cost here, 9208. So we list it here. Among these, what is the minimum cost? What is the minimum cost? So if we were at state 14 in our number 1, the associated cost was 9843. If we were at state number 12 at our number 1, the cost was 9208. So these are the previous costs. These column are the previous cost. This has nothing to do with whatever calculation is happening here. Remember, these are taken from the previous, this column, previous hour, this column. Okay, 9208, 9843. And we have only saved 12 and 14. Okay, 15 is not saved. 15 is not saved. So 12 and 14 are only there. So you see, either it is 9208 when it is 12, when it is 14, it is 9843, and the same pattern goes on. Same pattern goes on. Okay. So you see, we have the P cost available here, production cost. Next, what is, okay, so when we try to calculate F cost Ki, we have to take the minimum. Remember the DP algorithm? There was a term min at the very beginning. There's a minimum of L. Okay, so we have to minimize these costs, and that has to be stored in F cost. So what is the minimum cost among all these? Let's check. So that means we have to add, to have this F cost, we have to add this plus this plus this, that will come here, and either or other hand, on the other hand, we have to add this production cost plus this plus this. So simply the 0 is there in both cases. So among this plus this, or this plus this, the minimum one should be this plus this. So that is actually being listed only. We don't have to list this one. We don't have to calculate this one. Okay, or we don't have to print here. We compare these two. We compare these two summations. Whichever is minimum, we will pick it and we will store it. The other value is not required to be stored, because that is not the minimum among these two alternatives. Similarly, from 12 to 14 and 14 to 14. Okay, so the combination is this. How we are going to choose it? Now we have to choose unit 1, 2, and 3. All of these 3 will be there. So unit 3 is the least cost. Pick the maximum from it. Then jump to the highest cost unit, pick the minimum from it, and the remaining one should be taken from the intermediate units. So that gives you 530. Calculate the production cost. The transition cost from 14 to 14, there should not be any transition cost. From 12 to 14, there should be some transition cost. So from 12 to 14, this bit will be updated for unit number 1. So that means unit 1 startup cost has to be included, that is 350. So now the F cost, it is taken from the previous slide, already stored. So you just simply copy and paste them similarly like this. And then you add up and you check. If you add this plus this plus this, how much you get? And if you add this plus this plus this, how much you get? In this case, we see that this one is lower when we compare this value and this value over here, which is not mentioned here, of course. So we pick the minimum among these two strategy. Similarly, we do it for transition 12 to 15. Here also we do the ELD part. So we pick the 300 first from the least cost unit. Then we pick the minimum from the highest cost unit. We also pick the minimum from the next highest cost unit. And then we pick the remaining from the remaining unit number 2. And every time we have to check that all the values lies within their minimum and maximum limits. Okay, all the time we have to check. So all values are satisfied. The production cost is calculated. The state transition cost from 12 to 15, the transition cost is there. So 12 to 15, that means from 0110 to 1111. Now unit 4, it doesn't have any transition cost. It doesn't have any startup cost. So only startup cost is this 350. So we have to choose it. From 14 to 15, what is 14 to 15? Let's write it. 14 to 15, this is 14 and this is 15. We have to turn on unit number 4, but there is no startup cost, so 0 startup cost is there. Again, you add this one, and this one, you get this. You add this one, and this one, you get some value. Compare these two. Again, after comparison, it is found that this one is lower, so we store it. Then we have found all the combination costs, and we find that, well, again, this transition is the minimum. So the progress would be 12 to 12. So our 1 and our 2, we still remain on the same state. We still continue with the same state of 12. That means we still decide to turn on only unit 2 and unit 3. Unit 1 and unit 4 are off, but we choose to have these two stored, the two least cost strategy, and that is still 12 and 14 are the winners after comparing these three. Okay, so now we proceed to like this. We proceed to our number 3, our number 4, up to our number 8. Okay, and we try to find out the solutions. So now in our number 3, the load is further increased, but luckily the demand is such that the 12th state is now also unable to satisfy the demand of 600 megawatt. So state number 12 is not a feasible state now. Okay, state number 12 is not a feasible state. State 5, of course, it is not a feasible state. So only 14 and 15 are feasible. So our number 3, you have to make less calculation. That's good for us. Okay, so the previously saved state will come from the n value in our number 2. So the n value in our number 2 is 12 and 14. So the L value is now updated, our 12 and 14. Our K is now 3, load is now 600, feasible state 12 is also excluded from the feasible state, again due to the capacity limitation. So now only transition from the previous state, saved state is 12 and 14, these two state, and the state where we can have our transition is 14 and 15, those will go to I. So only 14 and 15 are now listed. So you can either have 12 to 14. I mean, you can have the transition now from 12 to 14, 12 to 15, 14 to 14, 14 to 15. So these 4 combinations are possible. So which are listed here. So if you are, again, I think by now you should be able to do this. So I'm not going to discuss in detail anymore. So you choose the unit production, you take the P cost, you calculate the P cost for each of these transition production cost. The transition cost from 12 to 15, again, this is the transition. So from 12 to 15, there are 2 bits that are to be updated, but for the 4th unit, you don't have any startup cost. So only startup cost will be here for unit number 1, and that is 350. And your transition, you are having the transition from hour 2 to hour 3. Okay, so 350 is there. From 14 to 15, you don't have any startup cost, so no transition cost is there. From 12 to 14, again 350. From 14 to 14, of course, there is no transition, that you are staying on the same state, so of course no state transition cost would be there. Now the F cost K minus 1L, you will take it from the previous table. So you take 19,856 and 20,491. So now you will see only these two: 19,856, 20,491, 19,856 and 20,491. Okay. So once you get these two, give these two, then if you add up, again you see that this one is the lower one among these two. This one is the lower among these two. Now you only have 2 strategies available, so you simply store them. This one and this one, only 2 strategies available. Progress, which one is lower? You don't have state 12 anymore, so your state 14 is the winner. Okay, this transition is the winner. You don't have state 12 to be chosen from. The state 12 is no more a feasible state. Okay, so you can't choose it. The one that you have to choose is this transition from 12 to 14. This gives you the lower cost. So you choose from 12 to 14. So this is the progress now. Our number 4, the demand has decreased. Again, 12 will come into play. Okay, because that is within the capacity of 12. 12 can produce maximum of 550. So your demand is 540. So 12 will again become a member of the feasible states, and you can do the steps, remaining steps. I hope you do the steps and you find out what is the progress. Finally, you find out, well, again, 12 is the progress. Okay, from 14 to 12, this is the progress. So from 14 to 12. Okay. Our number 5, the demand is further reduced. Again, you do the same. You check the progress. Again, 12 is the least cost strategy. Our number 6, though, the demand is now further decreased, and now state 5 also comes into play. That becomes a feasible state 2 because state 5 can produce a maximum of 300. So now there is more competitor in our number 6 because the demand has now reduced to 280, very low demand, and our state 5 comes into play. So now you have total 8 transitions possible from 12 to 5, 12 to 12, 12 to 14, 12 to 15, and similarly for 14 to 5 and so on. So total of 8 combinations or 8 transitions are possible. You calculate all these values, you list them, you get the F cost, take the minimum and include it in your progress list. So you see, now the new competitor is the winner. Okay, the new competitor is the winner. This transition is the winner. So when the demand is less, you can go for state number 5. You choose the 2 least cost strategy. 2 least cost strategy are these 2. Okay, so and this is the progress up to our number 6. Go to our number 7. The demand is such that still you can stay with 5. Okay, I mean, you can still include 5 among your feasible states. Do the calculations, and still it is 5. Still it is 5. So choose the last 2, the 2 least cost, not the last 2 actually. 2 least cost strategy are still 5 and 12. And the last hour is our number 8. 500 megawatt. Now it is beyond the capacity of state 5. So you can't choose state 5 among your feasible states. So you exclude it. But state 12 can still generate sufficient power to give a supply of 500 megawatts. So you include it here. And you do the calculation, and your final progress will look like this. So this is the 8-hour solution. 1, 2, 3, 4, 5, 6, 7, 8. This is the transition. This is your search strategy, and this is your final. So this, in this manner, you will complete the search strategy. And for an 8-hour problem, you have to do this much of calculation. Okay. And remember, this is only case number 1. Inshallah, in the next recording, I will start the case number 2. Okay, that will be a little bit more interesting, but actually the steps are almost identical. Okay, steps are almost identical, but your states that will compete will be a little bit more in number, because now in the enumeration scheme all the states will come into play. So you don't have to go for the priority scheme, but when you choose the state, of course that state has to satisfy. I mean, now the allowable states are all the states can take part into competition, but in the feasible state, of course, only those states will come into play which have sufficient capacities. Okay, so we'll take this inshallah in the next recording. Okay, so please go through the lecture, because probably very soon I am going to post another recording on this remaining slides. Okay, so till then, stay safe and sound. Assalamu alaikum.